So, hi everyone. I'd like to once again welcome all of you to the Pi seminar series dedicated to dedicated to like advancements in scientific machine learning. And today we have with us Dr. Shuvayan Brahmachary, and he's joining us from Shell. Dr. Shuvayan Brahmachary received his PhD in Fluid and Thermal Sciences stream of Mechanical Engineering Department at Indian Institute of Technology, Guwahati in the year 2019. Following his PhD, he worked as a postdoctoral researcher in the Department of Aeronautics and Astronautics at Kyushu University in Japan until 2021. Starting January 2022, he worked as a postdoctoral research fellow in the Department of Informatics at the UM, Germany. Presently, he is working as a scientific machine learning researcher in Shell, Bangalore, and his research interests include scientific machine learning, computational fluid dynamics, and optimization. And today, the talk Dr. Shuvayan will be discussing to us will be on the topic large language models as evolutionary optimizers for industrial problems, with a particular focus on a novel approach that was introduced recently, which is LEO, which is a short form for large language model based evolutionary optimizer, which leverages unique strengths of LLMs for numerical optimization. So, without wasting much time, I'd like to hand over the platform to Dr. Shuvayan for the rest of the talk. Thank you.
Hey, thank you so much for the kind introduction. Yeah, it's truly I'm grateful for for the invite for presenting this work, large language models as evolution optimizers for industrial problems in the Param-Intelligence seminar series. For those of you who don't know, this is actually a collaborative work that we have done in the recent past. Us as a scientific machine learning team, as well as Ameya Jagtap, right, who was at the time at the Brown University and since then has moved to WPI. All right, so without taking further time, let me go on with the presentation. Please feel free to stop me during this presentation. I would like to keep this engaging. And yeah, right. So before I present my work, I would like to give you a cautionary note. This presentation is going to be a direction towards future research. Please do not take this as a means for future investments, right? Right, just as a disclaimer. All right, it's only fair, I introduced my team to you. Us is the scientific machine learning team, which is headed by Kaushik Kalyanaraman. And as you can see, all of us wear multiple hats and have different skill sets, which allows us to, work on different kinds of problems. I believe you would appreciate the kind of work that I will be showing in the coming slides. All right. Now, what about the focus area, right? So as far as the focus area is concerned, our team primarily is concerned with, complex problems, complex system technology, climate transition technology, and neural manufacturing system. Now, you might at this point of time, wondering what is neural manufacturing system, because at the time when I heard it, it was not quite obvious to me. So neural manufacturing system is, in a very simplistic form, is the digital counterpart of a very big manufacturing system. So in Shell, its day-to-day operations involve a lot of sectors from upstream to downstream. Say, for example, exploration and extraction, production, refinement, production of chemical compounds or lubricants, all that daily operations requires a lot of physical processes. Now, what we try to do is, to create a very inexpensive, fast, that is, and reasonably accurate neural network surrogate, which can give you the, the quantities that you're interested in. For instance, one of the subsystems in the entire manufacturing plan could be, a heat exchanger for that matter. Now, in a heat exchanger, which is predominantly determined by or governed by heat transfer, in that case, you would be interested in the temperature distribution. So, what we are trying to build is, let's say a neural surrogate which can give us quick temperature distribution, right? So yeah, that is what we mean by the neural manufacturing systems. Now, this image, clearly describes that philosophy, right? So right from exploration, which involves processes like seismic inversion, and then extraction, and then satellite imagery, which can capture the evolving landscape of a town, and then we have subsurface property emulator, and LNG plant, carbon capture, and so on and so forth. So yeah, this image is kind of a highlight as to what kind of work that goes on, and the kind of sectors that we try to target with a neural surrogate. Okay. What about the approach, right? We are pretty much method agnostic. That means we have a plethora of approach that is available to us. And depending on the problem at hand, we will find the suitable problem, a suitable approach. It can range from differentiable physics, something that use a solver in the kind of a loop approach. We can use something like a neural operator, graph machine learning, scientific machine learning, and then of course, deployment of certain approach to production for production, right? Full stack ML. Right. And one of the segments that you can see here is the novel applications, which is where Leo comes in. This is going to be the predominant focus of today's talk. What is essentially Leo, right? So that brings me to this work that we have done, and it's presently published in archive. So you're free to have a look, and feel free to reach out to any one of us. This is the bigger scientific machine learning team. And as you can see, one of the collaborators is Ameya Jagtap. As I had mentioned, this was a close collaboration with him. So that work is named as a large language model-based evolutionary optimizer, reasoning with elitism. So I'm going to be describing what elitism means in this context in the coming slides. All right. So as far as the contents of the presentation is concerned, I will start with the very basics because I understand the audience might not be a optimization heavy audience. So I would like to keep it fairly generic, and that is going to warrant some introduction of keywords related to optimization theory. And then we will quickly move on to a motivation that is going to introduce as to why we went about this approach, right? It is not largely a I mean to say this is mostly a curiosity-driven experiment that we did with large language model because we wanted to explore the reasoning components of it and if its ability to see if it is able to come up with better solution, right? And devising an framework is not sufficient. You will have to benchmark it, right? So yeah, we did a lot of benchmarking here as well, and I'm going to be talking about the extensive benchmarking we did. And finally, I believe you would also be curious about the applications to shape optimization, heat transfer, multi-object optimization, or high-dimensional problems. And towards the end, I'm going to be talking about the reasoning component of it, whether there is a substance behind all the entire framework or it's just a framework that does seem to work. I'll be talking about all of that. All right, now coming to the very basics, let me start with the decision variables. Well, these are the variables, as you probably have guessed. These are the variables that gets controlled during an optimization process. These are the ones that gets perturbed from one iteration to the another one, and ultimately arrive at the optimal solution, right? Variable bounds. These are the bounds within which I would like to restrict my decision variables. My decision variables cannot escape that bound. Objective functions are essentially a function that needs to be maximized or minimized. For instance, I would want to buy a car which gives me most amount of comfort or most amount of mileage. These are my objective function. Again, constraint. Constraint could be an equality or non-equality constraint. For instance, I want to buy a car, but I cannot spend more than a certain amount of money. That is going to be your constraint. Right. That is fine in terms of a toy problem, but let's look at some of the benchmark optimization problem, like they call it, right? So I'm showing you an example, the Rosenbrock problem, which is a very famous problem that is being utilized in the literature. This is a 2D optimization problem. The first equation that you see here, your function is dependent on two independent variables, x and y's, and your x and y's can vary between certain bounds. And the idea would be to find out the values of x and y such that your fx comes out to be the least, right? And there is an extension of this 2D Rosenbrock problem to n-dimensional problem as well, something that we will indeed tackle as we go ahead. So yeah, that becomes really challenging, and this is not at all trivial. And yeah, we are actually trying to find solution for this problem as well. So yes, let me also show you what is meant by an initial guess. So let's say you want to optimize for Rosenbrock 2D, and I'm showing you the function landscape, the value of fx for different solutions. And here your solution means the value of x and y. So you start with an initial guess. You start somewhere at optimization iteration 0. That becomes your initial guess. And as you iterate using, say, any approach, gradient descent map for that matter, you, let's say, arrive at this one. This is your final solution. However, this is a local optimal solution. Local, because this is not the lowest possible function value. There is a global optimal solution, which is actually even lower than this, right? So this is only for the sake of illustration. I'm showing you initial guess, what is meant by initial guess, final solution, local optimal, and global optimal solution. Again, I'm keeping it very basic, and you might find it a bit trivial, but soon we will move to the crux of today's presentation. All right, then a population-based approach. You may or may not have heard about it, but you may have heard about methods like genetic algorithm and bee colony optimization, particle swamp optimization method. So those are population-based approach, because at any given iteration, you begin with a population of solution. You don't have one solution. So you begin with a multiple solution which are all different from each other. And then during the course of optimization, you arrive at a local optimal solution, local or global, whatever it may be. And I'm showing you 4 representative cases. And in each cases, you see I'm beginning with a population of solution. I'm sorry, I'm showing you 4 cases. Population size is 4. And in each case, you can see the trajectory of the progression of the solution, right? One of them is able to find the optimal solution, whereas the remaining ones is not able to do so. So that is the essence of population-based approach. Now, contrary to that would be a gradient descent or a gradient ascent method, which is a single solution method. You start with a single solution and you iterate towards the optimal solution. Okay, now what is exploration and exploitation? Now, these are very specific to optimization methods that are predominantly population-based. And your exploration essentially is a technique by which you want to generate solution that explores the design space. Let's say your design space, your x and y's and all those variables can only vary between a certain bound. Your bounds is represented by this box. And what you want to do is you want to generate solution such that it skims the entire design variable space as much as possible. So it is scattered, right? That is what is meant by exploration. And the idea would be that, at optimization iteration 0, or when it's starting, you don't necessarily know what are the good regions, which are the bad regions. So you explore the entire design space. That's the principle of exploration. Then we have the exploitation, right? Which is completely on the contrary. What is meant by exploitation is, let's say you find a good region, which is likely going to contain a global optimal solution. So you generate solution in the vicinity as much as possible to closely pack together so that one of the metals is, the global optimal solution or close to it. So that's the idea behind exploration and exploitation. All right. Now, if that's clear, then I will also highlight what is elitism-based guardrail. And I promise this is the last basic slide, and then we will soon move to the technical part. Okay. You may have heard about, guardrails in the context of large language model, but then we use it slightly differently. Elitism is a principle in population-based approach, which prefers the prefer or preservation of best solution at a given iteration. That is, let's say at a given iteration k, I have n number of solution, out of which I found out I have ranked them, right? I have ranked them based on their function values, and I want to minimize that. Of course, I'm going to see that certain solutions are the best. What I would want to do is I want to retain them in the next iteration. This is the very principle of elitism, that you retain the elitist solution, right? Okay. So now how does it work? Let's say at iteration 0, we begin with a random initial solution, and it's shown here. All right. What you would want to do is at the next iteration, if you look at the left, there is a global optimal solution, which I've marked in the form of star. Of course, you don't know the global optimal solution, but I'm showing it for illustration's sake. But for any random problem, you're not going to know it beforehand, right? Right. So at the next iteration, what you would want to do is generate scattered set of points in a hope that one of them lands close to the global optimal solution, or is reasonably close to the global optimal solution. And in this case, you see that one of them is indeed close to the global optimal solution. What you would want to do is you would want definitely this solution to be retained, okay, in the next iteration. That is the principle of uh, elitism. Now, this is the explore pool. In a sense that I'm trying to generate solution that explores the design space. Now, on the contrary, you would note that something opposite has happened in the exploit pool. I'm generating solution that is in the close vicinity, right? And as I've mentioned, there is a reason behind that. There's a method to this madness, as I would like to call it. Okay, so now how do I enforce elitism? I will port the best solutions from my explore pool, and I will take it to the exploit pool, right? You might want to ask at this point of time, why are you doing this? Why are you moving one solution from explore to exploit, right? How does it make sense? Well, the idea is in an optimization, it is typically seen that your exploit pool tends to find the optimal solution. This is because once you are in a good neighborhood of solution, you are going to exploit that region, and your exploit solution is bound to be close to this solution because all of these are going to be packed together. So it is bound that exploit pool is going to be uh, close to that optimal solution. So naturally, what we want is the best solution ported from exploit to exploit. All right. Once that is done, you would note that the population size on the exploit pool has increased by 2, right? So what you want to do is remove the 2 worst solutions so that you maintain the size of the population. So that's what I'm going to do. I'm going to remove 2 worst solution. Okay, and this number 2 can be any number, right? Of course, it has to be less than the population size. Okay, and the next iteration goes on. You then generate yet another set of solutions, and then you see your exploit pool has generated a solution close to the best solution, which is closer to the global optimal solution. So that's how this process goes on. Oh, I think I forgot there was one more basic content, but yeah, I'm going to go through it rather quickly. This is the multi-objective optimization. Well, what I've described so far is the single objective optimization, where you have a single objective, you have a set of decision variables, you know your constraints, and then you start and you iteratively find out your optimal solution. Well, many problems don't necessarily pose themselves in the form of a single objective optimization, right? It is indeed multi-objective, and it can be 2, 3, or whatsoever. Now, for the sake of illustration, I'm showing you 2 objectives. Let's say minimum environmental impact and maximum oil production. Now, these are conflicting objectives. That's the key word here. Conflicting objectives. And in that case, you're unlikely to find a single solution. What you would get is a non-dominated solution, right? non-dominated solutions are the one that is dominate the poor solutions, which is dominated shown here. And this is the front of non-dominated solution that you get at a given iteration. Now, as the optimization progresses, you'll note that your optimal solution, the front of optimal solution, arrives or converges to a single front. By single front, I do not mean single solution, a stable front of solution. That is known as Pareto optimal front. So what we try to do in this work is use Leo to find the Pareto optimal front for multi-objective problems. Okay, and when we benchmark it with using NSGA2, which is a seminal work which was done back in the 2002 by Kalyan Moedeb, and I said racked hundreds and thousands of citations. It's an amazing piece of work. And then there is the stochastic gradient descent, Adam, as you may have come across fairly recently, LBFGS, simulated annealing, and CMAES, and Cobila. So yeah, so these are the approach that I will be talking about when I will compare Leo. Right. So what was the motivation, right? It may not seem very obvious at this point in time. The motivation is whenever you are dealing with a simple problem, like this sphere problem, which has a single optima, then it's all good, right? You use a you use a gradient-based optimization. You start anywhere, and you will arrive very rapidly at the optimal solution. But that's hardly the case always. You will have many a times where your solutions are going to be, stuck in the local optimal solution. As you can see here, Rosenbrock function, right? It has multiple optima. Most of it is local, and there is this region where you find the local optimal solution. And then there are problems where you will have multiple global optimal solution, like the Himmelblau function, right? As you can see here, it has 4 distinct optimal solutions which are all equal, and they are scattered at different regions. So the idea is not only to arrive at an optimal solution, but to identify as many global optimal solutions as possible. So that's the key here. It won't be possible using gradient descent because you see it's a single solution based method. You start with a location, let's say somewhere here, you would be finding very quickly one of the solution, let's say. But it's equally important to find all the possible optimal solution. Right. So I hope the goal is clear. What we want to do is, devise a framework which is predominantly curiosity driven, which uses a large language model as the workhorse for these complex problems, not just a sphere function, but necessarily a much more multimodal problem. All right. Okay, so I think it is also good to give credits where credits are due. Our motivations were also driven by these seminal work fairly recently in the year 2023. As you can see here on the left, Google DeepMind came up with this work, large language model as optimizers, which is also an population-based approach, but they have predominantly used it for combinatorial optimization, right? The traveling salesperson problem. But the idea there is to optimize prompts such that you arrive at a better solution. Our approach is completely different. We have devised a very generic framework, which is problem agnostic, works for single and multi-objective optimization problems, well for single and multiple variables, and it is prompt, rather it's prompt independent. We have seen it for using multiple prompts and it works. Of course, there are certain caveats to that, but yeah. And on your right, you can see this work by NVIDIA, which is termed Eureka. Again, this was an amazing work, which uses AlexGym as the physical simulator, where your AI agent, which in this case is a large language model assisted framework, which teaches this robotic arm to spin a pen around its fingers, right? This is again an amazing work where the entire workflow, right from feeding inputs to your robotic arm, taking its output, and then giving it certain rewards based on the action that it has taken. The entire workflow is controlled by the large language model. So as in essence, it is an agentic AI kind of a framework. And at this point in time, we thought, okay, why not have a agentic AI-like framework, but it is going to be entirely for optimization. So that gives rise to Leo, right? So let me then introduce you to the framework of Leo. So this is going to be a very top level description of Leo, right? I'm going to go deeper, but let me begin with this rather simple uh, illustration. So again, as long as you're dealing with a large language model, you will have to prompt it, right? System prompts. In this case, we say that, okay, you are an intelligent assistant who can understand great technical details. You'll help me minimize two functions by taking cues from the given information. That's it. And
Shuvayan,
then you will feed the query. Yeah.
just question. Did we included this in the revised version, this image?
Yes. It is there in
In,
the revised version.
in the manuscript, revised manuscript.
Yes.
Okay,
It is there. It may not be there in the archive, but I'll have to check. But it is definitely there in the revised article.
okay. No, but anyway, once it get accepted, we can change it on archive.
Yeah. Yes. All right. So once you have a prompt, you will then feed that query to the large language model, and then you have to define a class. Your tokens gets encoded into digits, and after you get the output from the large language model, you have to decode it back to your textual format, and then the response that you get from the large language model is then used to perturb the decision variables. That's the keyword here. The only change that a large language model does is that it controls the decision variables. Okay. All right. So that's it. Now let's take a deeper dive into the framework, because I anticipate that may not have been entirely clear. So this is hopefully is going to hit the point home. So you begin with an initial random solution, right? And that is shown by these blue scattered points. You see, the blue scatters points in the exploit pool and explode pool are same. It's at iteration 0. And then you will do the function evaluation. That is for these solution that you've randomly generated, not LLM generated. You would then do the function evaluation score. That is, I will find out the fx or fx of y. Okay. And I will then rank them. All right. Once I rank them, then I will come to the exploit pool. Let's look here, right? You can see there are global optimal solution as well, the green stars. And then what I will do is I will ask the large language model that have a look at this set of solution, these blue points, only the blue points. You cannot tell the global optimal solution, the large language model, the optimal solution. That's the entire point. You want to arrive at it, right? So what you would say is, these are my initial guess. Look at this set of points and generate a new set of points within bounds such that my new function value is lower. You see, there are different levels of details here. First of all, you're prompting the large language model to have a look at this set of solutions. So that is context. Second, you're asking the large language model to generate solution within bounds. That means you cannot cross the bounds, because that is going to be useless. Third is, you want the large language model to anticipate or generate solutions such that those new set of solutions are going to be closely packed together, that is exploitation, and its function value are going to be lower, likely lower. You don't know for sure because you have not done the function evaluation, but you hope LLM is going to be smart enough to understand that. All right. So that is what it does. You see the next set of points, it is able to find out a solution which has the lowest function value, and then it generates new set of solution by this orange color solution, which are closely packed together. On the opposite, you see, exploration pool has generated scattered set of points. It identified one solution which has the lowest function value, and then it generated solutions scattered in a hope that you will generate more and more solutions away. Okay, and then at this point in time, you remember I will enforce the elitism criteria. That is, I will find out which are my best solutions in the explore pool, and I will take it to the exploit pool. And that is what I'm done, and I'm done with the first iteration. So this cycle continues. I will then, when the cycle continues, I will arrive at the optimal solutions. Don't take my word for it. I'm going to show you the results. All right, let's have a look at the benchmarking with the state-of-the-art methods. As I mentioned, we tried this approach with multiple benchmark function because one test case is not going to cut it. You have to test it with multiple ones, and then you will also have to test it with multiple methods. So to that extent, we have taken the scaled sphere problem, Himmelbau, Rosenbrock 2D, sphere 2D, Beal function, and the Goldstein price problems. And for all of this, I have mentioned the global optimal solution, and I've also indicated the bounds. Right, and again, the bottom table shows the performance of the benchmark functions, different methods with Leo. Leo is at the end. And I've also indicated the global optimal solution. You can take a quick look and you can see, Leo is outperforming stochastic gradient descent, Adam, as well as LBF, no, not LBFGS, simulated annealing, right? Hands down, it is beating that. And it's doing quite good, actually. We were really surprised to see that, it does so well, especially with simulated annealing as well. When compared to methods like CMAES, LBFGS, and COBILA, it is doing better than COBILA. However, it is at par with CMAES and LBFGS. If you look at these are the mean values which were obtained by running this problem on 100 different times. So we are not showing you one single value for one independent run. We are doing it 100 different times and doing the statistical evaluations. So this holds. All right, let me also show you some qualitative comparisons. This is the function plot of the convergence overlaid on the function landscape. So I've done it for different functions. As you can see, I start with sphere problem. At iteration 0, you're somewhere away from the global optimal solution. Your optimal solution is there, but as you're converging, as you're iterating towards the global optimal solution, you're converging towards the global optimal solution, right? And this is the case with all of them. As your iteration progresses, that is, you're progressing from the red to the green, you're making strides, you're taking strides towards the global optimal solution. That is seen across all the 6 set of problems. We had certain difficulty with Goldstein price problem, but then we were able to fine tune the algorithm a little bit and then saw that, it does really well for all the problems. All right, but yeah, Goldstein price problem was the most challenging one to solve. All right, with that, let me take you to the applications. First application that we targeted was the nozzle shape optimization, right? You may have come across this problem. This is, again, something that is common for the CFD community, that is compressible fluid dynamics, in the high-speed flow regime. Now, as you may have guessed, to find out an optimal geometry, which requires me to evaluate the flow quantities, I'm going to require a flow solver, right? Something that evaluates my f of x. To that extent, I'm using an area Mach number relationship using the quasi one-dimensional compressible flow theory. It is a very inexpensive approach because we wanted to quickly demonstrate that it works. So we chose to do this. Next question is, how do you represent the shape of the nozzle? So we have a 2D axisymmetric geometry that is symmetric about the axis. So we represent the shape using cubic Bezier curve, and that gives us 4 control points, 1, 2, 3, 4. But we fix the first and the last control point because we want to fix the inlet and the outlet radius, right? So that is the geometric constraint we are enforcing to the problem. That means your in-between solutions are free to change. This is what is going to be controlled by the optimizer, right? So that's the idea here. And I've also shown you representative nozzle shapes for different cases. Okay. So now what is the objective function? What are we trying to optimize for? Well, the idea is given a boundary condition, we want to obtain a nozzle shape which gives us maximum uniform flow or least axial flow. That is, flow should exit parallel to the streamwise direction, and there should be least flow in the streamwise, in the perpendicular direction, right? So that can be easily done using this area Mach number relationship. All you have to do is ensure that the exit velocity is a ratio of the radial to axial velocity is lowest. So that is what we're trying to minimize. All right. So now if you look at the convergence plot, you can see that we have continued the optimization for 30 iterations, and very quickly you are able to arrive at the optimal solution. And these are some of the plots that we get, or shapes of the nozzle that we get from explore and exploit pool. Now, it is very interesting to note that in the exploit pool, all your shapes converge to a single shape, which is very close to the bell-shaped nozzle. So if you look at the theory of the compressible 1D compressible flow, you would see that the bell-shaped nozzle is actually the optimal shape for these kind of problems. And we have been able to find out that using this Leo framework. So that was really nice to actually observe that. Right. So now let's talk about the next application, which is the 1D heat transfer. Again, a very rather simple problem here. What we have here is a 1D governing equation for heat transfer, where on the either extreme of the 1D domain, you have temperature, right? Your TL, TR. Your TL is kept to 0 and your TR is kept to 1. These are non-dimensional numbers. So now the idea is, how would you find out the solution of heat transfer using optimization? How do you do that? Well, turns out you can use finite difference to represent this governing equation, right? So you have 1D steady state heat transfer with constant heat generation. So you can use finite difference to represent that equation. And all you would want to do is find out Ti such that the residual loss, the difference between these two quantities, is the lowest. So that becomes your objective function. So that is what we are trying to minimize for. Okay, and we repeat this problem for increasing dimensionality. If we start with 2 points, we increase it to 4, and then we increase it to 8. And you would note that when you increase the population size from 2 to 4 to 8, your solution tends to become slightly worse, right? Your exact solution is sufficiently different from the solution that you get from Leo. So yeah, that was one of the stark observation that we made, that this works fine for low dimensional problem, but for higher dimensional problem, it is suffering. Now, what is the reason behind that, right? Maybe it is indeed that Leo doesn't work for high dimensional problems, but one thing what we have to remember is that you have increased the number of variables from 2 to 8. However, we have kept the optimization iteration same, which is rather unfair because you're increasing the complexity of the problem, but you're not giving it enough time to solve for it, right? So what, as a rule of thumb, your optimization iteration is should be at least 4 times the number of variables, which means that I have to increase the number of optimization iterations just to make it fair. Okay, next problem, right? Then we have the farm layout optimization. That is, how would you arrange the wind turbines such that your annualized energy production is the maximum? Okay. Again, for this, you're going to require a flow solver, something that evaluates this quantity. To that extent, we use Flores. It's an open source library which you can use. And we repeat this problem using different number of turbines. We start with 2, make it 4, and then 8. And finally, we want to see, right, how well Leo is doing with compared to standard optimization approach. So we'll compare the solution using SciPy optimizers. So here on your right, you can see the optimal wind turbine layout. When it is 2, you can see the optimization or the turbine location is, at the extreme ends, at the opposite ends of in the shape of a diagonal. And that is also what is found out using SciPy. See, most of the optimal, by most I mean when it was repeated for multiple times, oftentimes SciPy said that you should place the wind turbines at these locations. Now let's say when we increase the problem to 4 turbines, then we should be placing according to Leo, we should be placing the turbines at the 4 extreme corners. And that is also what is observed using SciPy. Now, if you increase it to 8, I guess again, it is the same. But you can note that from the convergence plot, you are increasing the power as you're optimizing from an initial guess. You're able to get higher values, and that is entirely done using large language model. Okay. Now, I spoke about one of the issues, that is high dimensional problem, high dimensional optimization. What happened there, right? I didn't talk much about it. All right. So let me talk a bit about that. So if you remember, I talked about the n-dimensional Rosenbrock problem, right? Which has an extension to n number of variables. So the interesting part is we know the solution. The solution of the function value should be 0, right? For that problem. However, there is one key thing that we realize at this point. Its solution, that is the values of all the decision variables, is equally 1. Now, it might be easy for a large language model to come up with a guess 1, because during the training, it may have seen the number 1 more often than let's say number 1.23. So we thought, okay, maybe it is making some trivial guesses. Large language model is making some trivial guess. So what we would want to do is change the problem such that your optimal solution now no longer lies at 0 by adding a small perturbation to it. So what we will do is we will offset the optimal solution by a small value. I don't remember what those exact value was. It's there in the manuscript, but let's just say it is 1.23 or some 4-digit number, right? Okay, so that introduces certain non-triviality. Your optimization now your objective function value is no longer at 0. And that is very difficult for large language model to guess, because who could guess the optimal solution is going to be something other than 1, unless you just have a robust framework which finds that solution. So that's the point of this exercise. All right. So next thing would be to repeat the Rosenbrock problem for different dimensionality. So 2D, 4D, all the way up to 25 dimension, right? You can see the convergence. All of them show a unique trend. That is, if you increase the optimization iteration, your function value reduces. That is, optimization is in fact in play. However, the idea here is to show that there is a reduction in the objective function value. It will naturally happen for large optimization iteration. As I mentioned, when you increase the population size, you also have to increase the optimization iteration. That I haven't done here. I have kept it same. But as I mentioned, the idea is only to show that qualitatively, if you increase the population size, you are also going to incur higher values, but it will reduce. Objective function value will reduce eventually. All right. Okay. Then let's move on to the next application. I believe this is the last application, and then we'll talk about the reasoning aspect of it. If you have questions, feel free to stop me here. Right. For multi-objective optimization, as I mentioned, it is not very trivial as to how you would locate the Pareto optimal front. If you remember, I spoke about Pareto optimal front for conflicting objectives. So yeah, that's what we want to investigate here. To that extent, we have two functions here, ZDT1, ZDT3. These are very famous benchmark problems for multi-objective optimization. And for those problems, you'll get a Pareto optimal front. For the ZDT1, you get a continuous set of solutions, where ZDT3, you get a fragmented set of solutions. So it was very important for us to see that if Leo does indeed work there. So I'm not going to go to the details of this framework with the small changes we did, but your Leo modular is able to indeed come up with solutions that closely matches the Pareto optimal front generated by the NSGA2 PyMo solution. That is again the open source solver, right? And that is also true for ZDT3. So that was again a relief to see that Leo not only works for single objective, but it is also working for multi-objective optimization. Right. Now let's talk about the final segment of this talk, that is LLM reasoning. If you look at the original work, which is done by DeepMind, that was you have to give them the credit to even think that optimization could be done using a large language model. But if you read closely, they don't explain the reasoning part of it, right? So we thought, okay, maybe devise certain careful experiments which will highlight that this is the LLM reasoning to generate good solution. It is not just random. Okay, how do we prove that? Okay, you see, in the Leo, we provide context. That is, we show the large language model that at this given iteration, these are my solutions and its function values. Based on this, you anticipate or you generate solutions such that in the explore prompt, they are scattered. Okay. Now you might be asking at this point of time, maybe there is no method here at all. It's just as good as a framework which generates random scattered set of points. So to prove that, we devised another framework, which is Leo R&D. That is, we will not show it the context, and we will not give it the guardrails. We will ask, you generate scattered set of points. Okay, so the essence of the prompt remains same. It's just that we have taken away the context. Now, for the exploit prompt, we do the same. For Leo, we will show it the context, but and we will ask that you generate points such that they are close by and your function value is reduced. But for Leo R&D, we will not do that. We will only ask, generate a new set of points which is close by to the lowest possible or the best possible solution, right? So at this point in time, we wanted to test, okay, which performs better. Is Leo performing better, which sees context and which has guardrails, such that it is able to reason to better solutions, or is it Leo R&D, which does not see the context, but it is still being asked to generate scattered points and close by points and so on and so forth. So if you look at the convergence plot, you'll note that as soon as I'm progressing, as soon as my optimization iteration progresses, I am very quickly able to converge to the global optimal solution using Leo. And that is not seen using Leo R&D. You see, it is even struggling to even converge. There's some convergence, but then it struggles to get to the optimal solution. So that's one level of reasoning. That is, it is generating good candidate solutions, which is able to find good solution. Now, the surprising and part of this study was these set of plots. In the explore pool, I've talked about explore pool and exploit pool, right? There is some reason to believe there will be convergence in the solution in the exploit pool, because once large language model identifies a good solution, it is going to produce solution close by. So you're converging to a solution. In the exploit pool, there is absolutely no reason to arrive at a convergence, or one can expect that your solution is just going to be scattered all the time. But that's not what we observe. You see, when we start with optimization iterations, the density estimation plot is significantly away from optimal solution. But as we progress, your exploit pool tends to move closer to the optimal solution, which means that even in the explore pool, your large language model eventually knows regions of interest that, okay, these are the regions I should be, generating solutions from. And that is what we have observed here. And that's the tendency you don't get in Leo R&D. So yeah, that was yet another verification, and with which we are able to claim that, it is indeed a large language model which is reasoning to generate good candidate solution. All right, I guess that leaves me with 5 minutes. Right. Okay, so the graphics have been slightly overlaid. So yeah, what are the conclusions? I'm not going to go through them in details. Let me tell you, this is rather a curiosity-driven investigation that we started with, ended up seeing that we have a framework which is rather problem agnostic. It is reasoning towards generating better candidate solution, which helps in faster convergence, as we have seen. The entire framework is built on the principle of survival of the fittest, like most population-based approaches are. And we enforce that with the elitism criteria. We see that single and multi-objective optimization works. And also we have expanded or tried this approach for different applications of industrial setting. The only cons at this point of time is the slightly poor convergence for the high dimensional problems. And that is something that we are presently working on. And yeah, we have some promising results using certain approaches, but it's presently not out yet. Hopefully soon. All right, that was me. That's my time. If you have any question, please let me know. I would be happy to answer.
Thank you, Dr. Shuvayan, for a wonderful talk on Leo. And now the floor is open for any questions. And if any of the participants, if you have anything, please feel free to unmute yourself and ask the question. So just to have one question from my end, it's like so you did discuss about single objective optimization where the explore and exploit happen parallelly, right, side by side. So, so every time you talk, you said that from the explore pool, it kind of transfers the candidates to the exploit pool, and so every time when you're doing that, how does the repopulation of that explore pool happening? Because I know from GA that you have the population getting generated, and you just discard the rest of the population that is not needed for the next iterations. So when you have such kind of a framework where exploit is always taking the best one from the explore, if I'm not wrong, then how does the new population for the next step of iterations get generated for exploration?
Yeah, good question. Let me take you to this slide here. So at this point in time, you see I'm at iteration 1 and I've generated explore pool and exploit pool. As you identified rightly, I will take the two most promising solutions, or K number of promising solutions from explore to exploit. And that leads to a difference in the population size. This is now a deficit of 2, and this has additional 2 solutions. So what we would want is before we move to the next iteration, we want to keep them same. So what we will do is, once we port it to the next, we will remove two worst solution from exploit. So that's what we are doing. That's how we maintain the balance between exploration pool and exploitation pool. And at the end of this is uh, what we have. We have the old solutions and the new solutions. So what we will do is we will filter them based on the ranking, and we'll retain the top uh, top n number of solution, that n being the population size. So in this case, it is 8. So that's how the operation works.
Okay, and also the prompt that you mentioned that you're giving to the a large language model every time for the new set of candidates to be generated.
Yes.
Are you giving is the prompt that you're giving conditional on the exploitation pool, if I'm not wrong? Because exploitation is the most elite class of population, right? So whatever conditional thing that you're giving, the data that you're giving as a prompt for the next step, it is from the exploitation pool, if I'm not wrong, or is it from both? Is it a combination of both?
Right. So the prompt largely remains same for exploration and exploitation, and it happens for both. The only thing that is different is in the explore pool, I'm going to prompt the large language model with the context, and I'm going to ask generate solution to such that they're completely different and scattered set of values from the above ones to explore away regions. On the contrary, this is going to change. Okay, I didn't include it for the exploit pool. I'm going to say that generate close by solutions in the close by regions to minimize the loss function. So that's the only difference between exploration and exploitation pool. But you're right that this happens for both explore and exploit.
Okay. No, I was just wondering, like, does it make sense to just give only exploit, because you know that the best candidates are always there in exploit pool. So will it help it in a better way, or do you think that's not very helpful, or something that you have not tried?
Well, but we did try it, yes. One of the
Okay.
combination was that we would prompt the large language model with exploit, and when it
Okay.
comes to explore, we will just use a random algorithm. But it turns out the convergence was poorer.
Okay.
Right. Yeah.
Sure. Thank you. Thank you.
Shuvayan, just one comment.
Yeah.
Basically, recently we worked on the methods that can actually handle the high dimensional problems,
Right.
and we have seen some really good results. So I think we can use this ideas here just to
Oh, okay.
overcome these one of the limitations of all these LLM based optimizers. So maybe we can
Oh,
discuss this sometime later. So
Amazing. Yeah, would be up for a discussion maybe in the coming days. I mean, so if I get it right, this is an approach which does not use large language model, right? And
no,
you want to see if
yeah, I mean,
okay.
if we can actually pull these ideas into this framework and
Hmm.
let it work for high D problems.
Sure, yeah. Actually, that's something that we are also investigating in parallelly.
Okay,
Yeah, it
okay,
would be nice to, yeah, good.
sure. Okay. Thanks for your talk.
I
Yeah.
think there is a question by Akshay Anand in the chat box. Akshay, like, if you don't mind, you can also like unmute yourself and ask the question if that's fine for you. Otherwise, I can read it out. Yeah.
Um, yeah, am I audible? I was having some mic issues. Not sure.
Oh yeah, you're audible. Yes, you're
Oh,
audible.
cool. So very interesting talk. I missed the first few minutes, but I was
Mhm.
just curious on how does the Leo handle the balance between the exploration and exploitation part. I think you covered the part of it, but with the question that Siddharth was asking, but I want to kind of emphasize on generally speaking that usually LLMs are trained on to be creative on creating kind of diverse outputs. So
Mhm.
does this model provide an advantage over local optima or some sort?
Yes, it certainly does. You see, so if I will take you to this illustration here, so for this Himmelblau function, you can see that there are multiple global optimal solutions, and the idea would be to locate this optimal solution and do it in a way that such that it does not get stuck in the local optimal solution. We were able to do that not only for Himmelblau, and we are actually doing it for all the problems.
Okay.
This is not what we observed when we used gradient descent. We saw that it was getting stuck. The convergence was poorer, except for scale function and the scaled sphere problem.
Yeah, that's interesting. Thank you.
Sure.
Right. Thank you. I think we are like pretty much done with all the questions, I believe, from the participants. So once again, I'd like to thank Dr. Shuvayan for having your time. Like I believe it's late at night back in India, so thank you for sparing your time to share this information with us. So thank you.
Thank you again for having me here. Thanks to Ameya for giving us the invite. As I mentioned, it's an honor for us to present in this seminar series. So yeah, happy to do that.
Thanks.
Thank you. Thank you, everyone.
And yeah, we can catch later.
Absolutely, yes.